Welcome back to our Scala to Spark class, and we are going to continue looking at various methods and ways we can pre-process data for machine learning applications, but also for other analysis, basically different tools that Spark provides us for basically transforming our data into some other data, you could say, in general terms. So we'll look at work with continuous features. So what does it mean? This means we have continuous features are basically numbers, right? They're values. You know, if you see just a single line, you have a just continuous line of numbers, right? From positive to negative infinity, depending how you look, right? So what we can do, what's very commonly done, is something called bucketing or binning. We basically transform the data into categories, basically, right? Second thing we can do, which we already did a little bit, we can do scaling, right? To basically, so to say, squeeze or normalize data. So let's look at bucketing, right? So, or sometimes called binning. By the way, there is a very nice glossary, right? So idea is this: we have a x-axis of values, right? Maybe x-y-axis, right? But we bin or bucket by just by x-axis here, right? We just put them in bins, basically, these values. So there's a really nice developers Google glossary for machine learning, which is quite nice for this for explanation of different terms, right? Of these ideas. Okay, so we'll use bucketizer, right? And so what do we need to provide? We are going to say what ranges, where do the numbers, which bin the numbers go in. You have to provide this, so to say, the boundary values, right? Where, let's say, it's bucket 0 or bucket A, bucket 1, bucket 2, bucket 3, and so on. So classical reason for doing so would be, let's say you have a person's weight, right, and you need to predict, right, some value, but you don't you won't actually have buckets. It's typically done to labels, to the answers, right? You want to say, instead of a numerical guess, you want to have a category guess. So you say overweight, average, or underweight, or you could have, of course, more categories, right? So what are the tricks? What do we need to do is we need to set the borders. The only thing is, if we have our data, we need to have it, so to say, have to cover all the values, right? So okay, let's take a look at this. Okay, so we'll get a Spark. Let's get started, right? We already by now be a pretty good shape, right? So new Scala class, and it's day 34 already. So day 34. Feature transformation, I guess, right? Feature transformation, transformation, right? And the object add extends app again, and I'll get Spark. Well, Sparky, of course, all good stuff. Chapter 24. So working with continuous features on, well, also with categorical features and categorical. Okay, right. So we have Spark, and now you'll see a little trick in Spark here. We take a range, right? Spark range, select expression, cast ID as double. So it's casting, right? So what's happening here, right? So we need, of course, double, right? So we need to cast our numbers as double, right? See, ID as double, right? Cast ID as double. So this expression will create the double numbers out of this 0 to 19 range, right? So we can see this, right? Continuous df, right? These are just numbers, right? Of course, you can see the range here, right? Range function and, right? I believe from 0. I guess you have to do some transformation if you want to, start with something else. You have to have some expression for, add something. If you want, say, values from 0 to 200, you have to say add another expression to add the numbers to this 0. I don't think there's a, I guess maybe, is there start? Let's try it. Is there start? No, I don't see it. No, I guess not. Okay, so this range method does not have start. It just says end. right? So, but it gives you long, right, with a column named ID, right? From 0, an exclusive, so step value 1, so 19, 0 to 19, okay, we want doubles. Okay, so continuous tfidf, show, I'm sure you'll see these are doubles, right? And it will be called expression cast ID as double. Let's see if it's actually going to be ID, or is the column name will be ID still. Let's take a look. Oh, and I didn't want to do that. Data re3 again. Okay, while it's doing, compiling. So let's talk about this. So what do you need? So you have 3 requirements. Minimum value should be less than minimum value in your data frame. Maximum value should be greater than maximum value. And you need at least, of course, you need 3 values. Because why? Because if you have 3 values, let's say this, you know, if this is -5 and let's say positive something, you need, you know, you'll have 2 buckets from 5 to 10 and 10 to 250, right? In this case. So, okay, that all run. This is, I'll stop it basically. This is from previous or transformations. Okay, let's run this one. So you should have numbers 0 to 19 as doubles. Yeah, as you can see, these are doubles, of course, right? Okay, so it still remains ID. That's very interesting. You could, of course, rename it as you know, my ID or something here, right? Cast ID as double, right? And so, of course, on. Okay, so that we are ready to go. Let's create some buckets, right? So these are so. Right, you set its borders, right? So this is what you need. And it's pretty simple, right? You just say, of course, you probably want to do some analysis beforehand, right? What kind of splits would make? Maybe do some statistics here first, right? So, right, so you could do a negative value, right? And also you need to say how do you handle invalid values, keep, error, or skip, right? So let's take a look how this all works. And there's also, right, and there's a warning also that it's, you use a splits method, and again, that's, you know, that's why naming things is important in libraries. It's not technically a well, they're not actually splits, right? Technically. So we just say make an array or sequence. Any sequence will do. Okay. So why is this? This is gonna be minus 1, 5, 10, 250, right, and 600. Well, so what's gonna happen? So bucket from here, right? 1 bucket. 2 buckets, second bucket, third bucket, and fourth bucket. But since we're going to use continuous tfidf, right? Only this bucket will be filled, this bucket will be filled, and this bucket, right? There's no values 250 to 600 because we only have values from 0 to 19. Okay, let's take a look, right? So bucket there, right? So let's take a look, right? I'll see. I think you'll see quite nicely. This is a good example. So bucketizer. I like this feature, right? So again, of course, you'll see that these values, you know, so again, crucial part is that you need to have the minimum maximum value first. So you might want to, so you might want to check min and max values beforehand, right? You could, of course, you could even do it programmatically, right? Right, just check, of course. So bucketeer, I'll call it bucket, right? You don't have bucket df, maybe, okay, but I want, name doesn't like it. And we should see, so we should see 0, these names, basically the names basically are just, you know, numeric names, of course. We'll take a look. Will we keep? I think we keep the origin. Yeah, we do keep. Okay, so as you can see very clearly, the only things you need to check is what happens on the border cases, right? So 5 already. So it adds. So the border cases, right? When you look at our picture, where's our picture? Yeah, right. So it goes to the new bucket, right? To the new bin, right? So 5 and same should go for 10, right? Let's take a look. 10, yes, 10 is already in the third bucket, you know, this number 2, right? Third bucket is here, right? And then, of course, there's nothing in the bucket 3, right? I mean, you're free to add more buckets, of course, but it's not gonna, nothing's gonna happen with this particular set of data. Again, it's just a simple array. You just give it, right? Question is now, do you have any extra? There was some extra options, right? So this is a bucketier. This is a data frame, of course. Oh no, it's a bucketizer. We transform. Oh yeah, it's actually a bucketizer, right? So a bucketier, right? it's not a data frame, right? Data frame is here, right? Transform, right? It's a transformer again, right? And you give it a data frame. So you can, of course, you can use it. You can use it to some other data, of course, right? All at once, it wants a data frame. You know, data set of something, and it once gives you again out a new data frame. Basically, in comes one data frame, and you can use it to, you know, bucketize something. Okay, so that explains, I think, explains pretty well how it works. Right. Yes, what I like, this quantile descriptor, which is, I think, is more, maybe I think even more automatic, right? You say use approximate quantiles. So basically, you want to split, let's say, with you just need how many buckets you want, and roughly they'll be equally sized, right? You say, let's say you want 10 buckets, so you know, 90th quantile, right? So 90% of data will be below that. So the last bucket will cover the last remaining 10%, right? So you can see also, since this is approximate calculation, right? So how many you want, right? So let's take a look, right? So let's say you want five buckets, right? Right. So this is pretty good try as well, right? So on right, set 5 buckets, and it will create. It's like basically how many buckets you want, and well, and Spark will happily oblige. Okay, so we need, no, this is not, there we go. And, okay, what's happening? Bucketeer, right? That's a problem here, right? Not good, right? Fitted bucketeer, why doesn't fit? Transform, I think this is a mistake, I think, right? I think it should be transform, right? Oh no, bucketeer. Why is there a problem here? It should be, okay, we should call the same name, right? It's not, you don't rename it, so Q, I'll call it Q. Quant bucketeer, right? Okay. And why does it say fit? That's a good question. Is there another? Right. You know why? Because it has to learn, right? It has to learn, right? Quant, right? Because so quant. So again. So what's the difference? So yeah. So unlike regular bucketizer, right? Bucketizer, you first have to fit the data, right? Because you know, the bucket, this quantile descriptor, right? It has to quantile. It needs to, the model needs to learn the quantiles, right? You know, the distribution basically, right? That's why you need to do the fit first, then you can transform. Of course, you can do this. Of course, you could do this in one line, right? Of course, right? You could do this basically. You could of course do the same thing. Quant bucketeer, right? Fit cont df, right? And again transform immediately, right? The same thing, same exact thing. And show, right? I'll show, right? You know, so you'll see it's exactly the same as above, same as above 2 lines, same as above 2 lines, right? Of course, right? If you don't want to save this this bucketizer, again, it's still a type bucketizer, right? It's still, but it's not. At this point, it's ready. You see, this is right. Again, why it doesn't say the type, right? Quantile descriptor, right? And then it's bucketizer. Okay, so and you should see the results. Okay, while it's running, so we should see it in 5. So basically, you have to say, okay, how many buckets you want, and it will do it nicely. So So I would expect 4 numbers, right? The only question, is it exact? I think it's not. Let's see. Yeah, it's not exact. That's one kind of funny thing. You notice 0, 0, 0. Lots of ones. No, 2s, 3s, 4s. So there's 5 4s, right? And only 3 zeros, right? So again, because it's not you have to read the documentation. You can set the relative error. I think. Let's see. I think it's done here. Right. Input column, of course, right? And set relative error. I believe it's here, right? Yeah. Relative error, right? And let's see. How do you say it? Can I do just, it's double, right? So if I do 0.01, right? Let's see what happens. Right? Yeah. I don't want the big error, right? Will it work? Maybe 0, 0. We can put it, maybe if I do 0, it will be very precise, right? Looks like it doesn't really do much. Still the same. So 0 is actually right. You have to play around. So play around with this value. So play around with the relative error values. Okay, but I won't. No, due to time constraints, I won't play around with this too much. Okay, but let's move on to scaling. We already did standard scaler, right? So basically, it is all about getting our data into basically, you don't want, you have different features, right? Across, one value goes, one feature, one column goes from, let's say, 0 to 10, and one goes from 500 to 60,000, right? And of course, if you do some learning, you want to run your algorithms, the second column will be much more important, right? It will turn, again, but in real life, in the domain you are analyzing, they are both equally important features. So that's why you need scaling and normalization. You want the both features, this knowledge, right? This information to be equally important. That's why you have scaling and normalization, basically, right? So height and weight, right? So so height, right? And in weight in ounces, right? If you especially have weight in ounces, right, it will be much more important than height in feet, right? Because height values in feet, you have 6 feet, right? Or 5 feet, 6 feet, right? But ounces, weight in ounces will be huge, right? That's why you need scaling, right? So that's very, very important, of course, right? And there are many out. I won't, again, we only saw standard scalar, so I will just go to regular one, right? So, so, right, so there are, yeah, so this is basically, again, extra things you can explore on as need arise, on need to know basis, so to say, right? So we use a vector, right? And so we have 2 vectors in a column, right? So yeah, so basically you have 2 vectors. Basically, of course, you have 2 rows of vectors. Then, of course, you will, this 1 and 3 will be adjusted, and 2 and 4, basically. Meaning, think of them as columns, basically, here, right? So you do it, again, that's why ML Sparks library, right? You don't give to the extra, so you want, you'll need to have a vector, basically, right? So let's take a look. We use standard scalar actually here. So actually we did that already before, right? So we gave the it transforms, right? And also remember, we could also set it whether you want mean. You all had an exercise on this. There's also min-max scalar, right? So right, it'll basically say, okay, let's try this one, right? So let's try this one. We only saw a standard scalar, right? Remember, right? So this is what we only saw this. We only saw this. This is done. We did this in. I think day 33, I believe, right? Let me see. Control Shift F, standard scalar. Yep, there it is. Day. Not right now, but there should be more. Yeah, day 33, right? Preprocessing Scala. We did this in the preprocessing Scala, right? Okay, so let's do the our min-max scalar. Again, simple concept, right? You say zero again. You say what kind of distribution you want, right? Proportionally, this is going to be proportional one, right? And I'll always be 0 to 1, but we'll do something maybe slightly different. Set min, set max, yeah, very easy, right? And only thing is, right, I don't have a. You do need to fit. You do need to have fit first again, right? So I don't have the scale one, so I will. Right, X Control Z. Sorry about that. Right, so I'm not going to import it from here, right? Yeah, there we go. Come on, pick up. Yep. Right, so I don't have cont df will be fine, right? So cont df, right? And I'm gonna basically just do transformation directly, right? Fitted min max, right? So I'll just do it directly. I won't save any values, basically. Fit, and then of course transform, right? Scale cont df again, right? And of course show, right? So we squeeze our 0 to values 0 to 19 into squeeze into 5 to 10. So is this inclusive? That's only. Let's check. I think it's inclusive. Let's take a look, right? So we squeeze our values from 5 squeeze values inside. Only thing is, I don't think it's gonna work. Right, features, right? I don't have features. I have ID, but it's not a vector, right? So that's the only problem. I don't think it will work. Let's take a look, right? It won't work, right? I think we need to have we need to also vectorize put it into vector first, I believe. Let's take a look at that, right? I wonder if you could do it as a vector with select expression. I don't think it'll work, but let's take a look, right? So fit transform from 5 to 10, right? In the range. Of course, I'm sure you could probably write your own min-maxer. I mean, it's just a simple formula, right? You could say you need to find the mean, set max, right, and figure out what kind of offset and what kind of multiplication you need for your values. Let's take a look. I don't think it will work at all, of course. Let's take a look. How are we doing on time? We're doing good on time, so we'll have time to fix this. So we'll need to create a vector of this, right? Yeah, okay, yeah, you need a vector. Yeah, of class vector. Okay, right. So we used vector assembler, but I wonder if there was a right. Was there anything else? So okay, we need a vector assembler. Can we do it in one line, right? Transform, right? Right. Ah, okay. Yeah, you need assembler, right? So you just say okay. All right, let's do that. And set name as set output column. So let's do this, right? And of course, so how do I do it with single column, right? Well, why not, right? So, but I need a vector assembler first, right? So I'll do this, right? Of course, right? Val, right? Fortunately, of course. Come on, pick up. Come on. New, I guess I need new. Yep, okay, there we go. And of course, these are not the right columns, right? So what does it say? Doesn't like something here? Yeah, array, right? Yeah, of course, array. So that would be not a big problem, but the problem is, of course, yeah. So we need array, but we only have one ID, right? That's all we have, right? Single column, right? So that's the thing with many of these data transformations. So we only have a single column, but we still need to put it in a vector, right? So that's the only kind of like annoying thing, right? A little bit, right? So now of course transform, right? We're gonna transform. We don't need to do fitting, so we have to have this. So could we do this? Right, yeah. So if this is data frame, right? Yeah, we could do this basically. Right, but I'll save transform, right? Vectorized vector, well, vector df, right? Will be this one here, right? Transform, right? On the continue df, right? And and of course, one thing I want to do, since this gives you a really silly name, right? We want to do this also. Want to do set output column, right? Set output call, right? Right, and I'll call it, say, features, right? Maybe features, right? Feature, right? Feature. I'll do features, okay? Right, it's of course it's only one feature, but okay. And so of course I'll call it features IDs here, right? So it has to match, of course, right? All right, so we are ready to do on vector df, right? It will show it. I'll show it to you. Show, right? And we are going to do it here. Vector df and of course vector df. So again, lots of data munging and lots of data transformation. Okay, that should work, right? Yeah, so right. So let's take a look. Yeah, of course, it'd be nice to have it for single columns, to have option to work with, do it directly, but unfortunately does not, this ML library, at least the version we have, does not support it. Right? Okay, so as we can see, yeah, okay, great. All right, so this was our first, okay, so this is our bucketizer. Okay, so now quantile bucketizer, but okay, so this is features. So again, you see, basically all it did is this vector is basically just a, you know, single value vector, basically with one value, but you need this format again. So again, features, right? On min max output, I set output. So here I didn't min max. I should have put also input column, output column also, as you can imagine, right? And I'll call it set output column. Set output column, again, very common, right? We'll call it you know, scaled min max, you know, min max scale, right? And as you can see, it's very simple, right? I mean, very standard, 5 to 10, right? And I'll do maybe 12, right? You can see it's completely arbitrary, right? So it's up to you what you want to do here, right? So let's take a look again. Okay, as you can see, 5 to 12, easy stuff, right? Pretty self-explanatory what's happened here. Okay, let's keep going on. Let's go the other way, right? Working with continuous values, right? We did back. So now let's do categorical values, right? So right. So we probably want to have a numeric value again, right? So conceptually it's pretty simple idea, right? You have a text, you know, strings, right? And you want to map them to some numbers, right? So so the recommendation is to reindex every categorical value just for consistency, right? So basically when pre-processing, because of course encoding might change, you know, over time. So we will need to, we will want to, excuse me, index with string indexer basically maps strings to different numerical IDs, basically, right? Something like this, you know, green, good, bad, remember, right? Do I have any simple? I guess I'll have to take from this previous day, right? Pre-processing, right? I will want to open it up, right? Here, right? Where's our data? Yeah, I guess we can do these, right? Maybe we'll do some more just in case. I'll just copy them. Maybe we'll need some of these. still, right, and basically use this. So let's take a look at it. So idea is basically we'll have numbers basically out of some strings, right? So set input, set output again, right? And we should see some nice results, right? And we have, of course, need of course import it, right? This was remember, or we'll see. Okay, we'll see. It basically this simple df, right? You had good and bad, I believe, right? And so simple df, yeah, simple df, simple ml, right? So there won't be very many, you know, they're on one index basically, right? And I believe we already did one hot encoding, right? And we already did text encoding as well, right? Let's see. And where's your indexer? Oh, it's loading. Oh, it's loading the big data frame, right? But you can see, of course, good, bad is 0, good, bad 1, right? Okay, which one is 0? Why is it? I think good is 1 here, bad 0. We didn't really. Yeah, we said lab. Of course, I could also do green, blue, green, blue, red, right? If I do that, right? I'll change it, right? I'll change it here. That's why I like this method, right? Control D, right? I'll change it, right? I'll use color, right? I'll use color, right? And then should we have 3 values? So now we'll have, we'll have index for again for each value. Again, the only problem is this with this approach, of course, is these numbers. You have to be very careful to use them. It's like a typical, say, an error is to use them in some algorithms which need a numerical value, because green, blue, red, right? These values don't have a, so say, meaning, right? Numerical meaning, right? They're not ordered, right? That's one thing. So that's why one-hot encoding is usually used, right? Is preferable. But the problem is, of course, right? Yeah. Okay, right, you see 0, 1, 2, of course, right? Blue is 2, green is 1, and red is 0. Okay, so that's all good, but now we move on to, like I said, so one-hot encoding I think we did already, right? Was since it's sort of right now. So again, this is something we already did, right? So, right, so very often, right, we would encode, right, often, important, often categories are better, transform into one-hot encoding. So, meaning, so one, like flags, basically. Okay. So that's, we already did this before. So text tokenizing we already saw, right? There is also some interesting things. You can remove stopwords, right? Which of course, again, you could do it by hand, but again, there is actually a language, Latvian and Lithuanian, and unfortunately is not supported. So once we learn tokenizing, right, you can also remove some word combinations, right? Let's add tokenizing again, right? So freeform text into, you split by usually white space, right? And right, so we'll want to have the, things like that. You already did this before, so I'll add it basically, right? Right, so, but let's get our stop words, see if we can do it on our own. I don't think it's, so let's, English I think is supported, right? But we already did this before, so I won't spend time on this. Right, on tokenizer. Right, come on, our tokenizer. Right, come on, pick up. Come on, it's asleep. Port class. Oh yeah, there's a couple tokenizers, that's why. Okay, yeah. And false, right. So we want to see this. Okay, right, we have our nice little tokens, right, it worked pretty well, but we want to remove the common words, right, so that's what we want to see, right, okay, and by the way, you can do also regex, right, by the way, that's, you can see this example, right, so, right, so, set pattern, right, so this would do the same thing, right? This might be, I won't spend time on this, but again, remember regex is your friend, right? We can actually, you know, do quite, so we say, okay, split by, this is of course just regular white space, right? But of course, you might want to say maybe multiple white space, right? This will be something else, right? So this is just the same type of transformation. Right, we probably want something for if you're using regex. If we are using regex, we want something more complex, probably. Right, it's kind of like overkill. So overkill, so overkill here, right? Because that's happening here. So questions, of course, do you want maybe multiple, right? Maybe have one or more, right? You know, if you remember our regex 101, right? So, and so on and so on and so on. Okay, so RT, yeah, okay, right. So that's good, but removing common words, right? So Danish, Dutch, English, Finnish, we'll check. Right, load default stop word. Let's try this again. This is not course. Let's see what kind of data set it is, right? Maybe we can do it our own, Latvian, Lithuanian, because there are places, right? If you have to work with our local text, right? Very common task, right? Is of course you could do this. You could write your command, of course, yourself, right? I mean, I'm sure you could do it, but why write your own program if this is you know already supported, you know? So stop words removal. Let's take a look at this, right? So. Of course, this will work, right? But let's see what languages are supported up to date. Stop words removal. Okay, on. Yeah, let's take a look. What's supported up to, because this is when this book was written. Latvian was not supported, but maybe now Spark, right? 3.2. Yeah, Spark 3.2. Right. Stop words Wikipedia. Let's see what languages are supported. I want the method. What do we call it? Load default step words. Okay, load default step words. Load. What are methods we have? Loads default step words. Okay. Still the same language. Maybe Russian came. I think it's still same languages, right? Right. So we'll need to see what is it. It's an array of strings, so obviously we could do our Latvian one. So right, since the result is just an array of strings, we could load our own, right, from file. For example, I know Latvian one is here. Latvian stop words list, right, is here. Not here, GitHub. Let's see, no, this one here, ISO stop words. It's not exhaustive list, right? Use the stop word JSON. It's in a JSON format. That's the only problem. Of course, you might want to read it also in some other format. Oh, that's not my format. What is that? That's everything. That's every language. I don't want every language. Let's see. I want the Latvian stop words list. LV. stop words. Ah, yeah. I think Lithuanian also there. Of course, this is not a. Oh, I mean, this person who is doing this GitHub, it's not a. She doesn't speak Latvian actually, right? So they took it from some. So yeah, this one, yeah. So this is fine. I mean, these are okay, right? Words, but you can add your own basically, right? You could download this and of course add it yourself, right? You could just basically load from here, right? You could download this. Yeah. So for Latvian, you could download the text file from here, right? Right, and of course, and split into an array of strings, of course, right? Right. Okay, but yeah. So this is English text, so we will get rid of the English words. So probably something like off, in, and so on. You might say, okay, these are important. Well, they provide meaning, yes, but for analysis, most type of analysis don't provide anything meaningful, right? For some things they do, right? So this of course is right again. Stop words again. So stop words you want to curate yourself, right? Depending on use case, of course. All right. So let's see how it works. So we have stop words, right? So this is stop words remover. Basically, you say, okay, these are the words. This is an array of strings, right? So in what we are going to remove. So what we are going to remove, and of course also description out. That's we're going to input column, and I'll call it also, of course, set output column. Of course. Desk out no stop words. Okay, something like that, right? All right. Well, let's take a look. All right. So set, you see, as I said, off is gone. I should have false. Should have been said false, of course, right? Right. Okay. And what else? Yeah, you can see, of course, that some of the words are gone. It looks like there's space. You see, I think because the tokenizer, right? There's extra space here, right? So it's something that didn't. There's some extra data. It preserved the space, I think, right? So maybe a regex would have been better. Okay, right. So bag, right. Vintage. Okay, yeah. A is also gone, right? Because it's all right. So as you can see, it nicely clean. So what else can you do with stop? What else can you do with for manipulating text? Well, one of the common things is you want to have maybe go beyond single words, right? So something that's used in language analysis is, of course, n-grams, right? So if you have words of n-gram of length 1, it will be called unigram. Length 2 is bigram, trigram is 3, and so on, right? Usually, 4 gram, 5 gram, and so on, right? So you have 3 words, right? You want to have bigrams. So let's say Valdis teaches Spark, right? So you have a bigram Valdis teaches. And then second bigram will be teaches Spark, right? So you have 3 words, right? So, and again, so big data processing. As you can see, big data processing, made and made simple. Again, theory being, of course, that these words close by, they have some meaning, of course, right? So again, this is basic natural language processing basics. Basically, I mean, there's more advanced things, but bigrams, trigrams is what you usually start with. Okay, so we are going to do that. Right. All right. So, we can say unigram, bigram, right? We can do trigram, right? And right, can we do actually? Transform, tokenize, select the stream out, right? We need to select this, right? And could we combine them, right? So let's take a look. I'll do trigrams as well, maybe if we have time. Alright, oh, sorry about that. So need engram. Alright. So only thing is this is a tokenizer, right? Engram, right? So you need transform, right? And then show. Yeah, can we actually why do I need to do this? Why can't I just give it tokenized? I'm just curious, right? Let's run this. And then I'm kind of worrying why, because of course you may want to have multiple, right? I know why, because you probably are getting pretty big lists, right? Transformation, right? Yeah, because this is going to be what? It's a single column, right? Probably. Okay, right, all right. So, yeah, no, it works fine. Okay, so out of each column, rabbit night light, you get rabbit night, night light. Okay, donut, donut lip, lip gloss. 12 message, right? Again, you can see how simple it works by gram. And of course, unigram is exactly nothing changed, right? Unigram is basically, again, very nothing changed. Okay, so you can create this column of girl Emily kit. Right, so you can see very set off of for again, so you can do trigrams and so on. You can do trigrams, so trig would be again, it's you don't usually go beyond trigrams because you don't have too much, you lose a lot of you know, they become too rare basically. But okay, so next thing or last thing which we'll do today, I think we will do a count words, right? Yeah, so we will do it we want to see what kind of combinations. So basically we are measuring whether each row contains a given word, right? So it's a very simple way of basically normalize for different document sizes, right? So we can do a, you know, create a content classifier basically, right? So we can just simply count using count vectorizer. Again, that will be one way. There's also something called tfidf, term frequency inverse document frequency, right? Transformation. And so let's start with count vectorizer, right? So we fit, it finds the words in all documents and counts occurrence of those words in documents, right? And then it counts occurrence of a given word in each row, right? And outputs a vector basically, right? So every row is a document. So think of it, you know, a book or novel or just a chapter. But so each row is a separate document. Every word is, you know, every word is a term, and total collection will be a vocabulary, right? So those are all you can tune. You can have minimum, right, maximum, right, and also say how big a vocabulary, right? Maybe if you are doing work on Shakespeare, right, you will maybe want to set vocabulary size to 50,000. If you're doing something, I don't know, of Dan Brown, maybe 10,000, and so on, right? So depends actually, of course, on your needs, right? So very cool stuff. Let's see how it works in practice, right? Yeah. Right, on again, so a minimum, you know, at least one, right? Very small vocabulary, 500, right? Again, so why do you limit why do you limit vocabulary size? Because you'll have a huge your table will be huge, right? Because this will be you'll need to do a fit on show, right? This will be quite big, right? So the binary, where is it? Okay, let's see. Okay, well, let's take a look. Description out. we use with tokenized. We have which was this. We only have okay. So tokenized words. We use it on a description out. We're basically using it on this data, right? We can use on this data, right? You could of course also clean the without the stop words or so on and so on. Okay, so minimum term frequency. So basically means so. Obviously, this is kind of pretty much right. So term has to appear at least once, but on this term has to appear in at least 2 documents, right? So single use somewhere will not be shown, right? Basically, of course, you could say one. If you say one, of course, it'll be basically go through all it'll look at all occurrences. Okay, let's see what happens actually here. You'll see it in operation. Let's wait, it takes a while. No, it's not that big, but still okay. So what did we get out of this, right? First of all, you have 500. It's a sparse vector, right? And so what happens is this, right? So do we have any doubles here? Hot water bottle, right? So you see 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So rabbit, night light. Okay, so these are the 500 words. And here, okay, this is only 3, so this is nothing here. So girl, Felka girl, Emily kit. That's interesting. CD60. Apparently Feldcraft. Imagine is only here. Nobody else. Girl and Emily and kit is everywhere. But so you can see. Let's say water, right? Water is indexed. Let's see. 15. I believe it's 34. Again. The vocabulary. Let's see. I don't know if the book shows you don't see directly what the. So each of these indexes correspond to some word, right? Obviously, you can figure this out by hand, but I think there's also a way to output the dictionary, right? So can we output, right? Let's see. Can we do this? So vocabulary. Can we get it out? So fitted CV. Right, so we did a fit, right? Yeah, tokenized, right? And let's see. I think you can. Let's try it. Vocabulary. Yeah, it's an array of string. There you go. Right. So print line. Let's say slice. Let's see. We have some words. Message. Let's say slice. I don't know, 30 to 450, right? Right, for each make string. Okay, something like that, right? Okay, let's take a look. We can print out dictionary. Okay, or maybe I'll do this, right? So, or this index, right? We'll see what it looks like. Vocabulary. Right, so here I print index 30 to 49, right? So that's, I think so, right? Yeah. Until is not, until is not included, right? Right, words. Okay, so polka dot, glass, cases, tea, bottle, 12. Let's see, where is bottle? Where did I see bottle? So 12, right? That's 35, right? That indeed. So 30, 31, 32, 33, 34, 35, right? And bottle, where's that? This is 34 somewhere here. Okay, where's 34? Here, yeah, bottle, right? So bottle, right? So that's this one here, right? So 39 was, what's 39 would be hot, I believe, right? And water, I believe. Again, so you can of course print it out and see, right, what index it creates. Again, so it's all, you can get the information back. Again, it's a data transformation all the time, right? You need to, you know, the algorithms like to work with numbers, but of course, humanly, we want, of course, the actual words as well, right? So we preserve that as well. So better, this is of course just a count, right? And so in this case, it's mostly ones, right? So 0 is sparse. 0 means that this word does not occur. If there's some word which occurs maybe more than once, right, you could find those words as well, right? Okay, now it's just a sparse vector, right? So, but even a better way, well, more, so say more, for deeper analysis is something, we use something called term frequency, inverse document frequency. So idea is this, we have this term frequency, which is this basically, right? So, but we also have a weight, we divide by the document frequency, basically how often the word occurs in each document. So idea is this, the words that occur in a few documents, they are more important than the words in many documents. So that means like a word in or the or a or, you know, I don't know, girl, boy, for example, right? They were common words. They will have less importance than something like, I don't know, like what that word here, what we use, that what was it, Feldkraft, right? That will be probably have a higher. It will not appear too many times, right? Term frequency, but it's only in a single document, so it will be obviously more important. So if you have some strange word occurring many times in a single document, right, this will be considered, this is important for this, right? So okay, so it's, let's take a look at example. Right, so let's take a look at example, right? So it's built in tfid tokenized where this is just the tfd in, right? We select limit 10. Okay, right, this is just a processing step, right? We get something which is something in with red, right? Let's just show you an example, right? And then we will be able to, okay, we're doing this is long lecture, so I want to finish this. I want to end on this, right? We won't have time to word to vec. You'll have to read about that yourself. That's a very cool thing. So we should have you know, we have, this is just a filter. This is just a filter. Okay, yeah. So this is what we just a filter, right? That's we're gonna feed it in because we don't want to show everything, right? So right, so we are gonna basically hash each word and convert it to a numerical representation, and then have it. It's similar to count vectorizer, but it's right. Right. We lose some information here, right? But let's take a look here. What will happen? Control Z. Right, and we should see nicely 10,000 features, right? Right, so up to 10,000 words, right? TF out, right, and TF, right? term frequency in the IDF, right? At least you say, okay, it has to be at least in 2 documents, right? And then we can use it, hopefully, right? We can use it, right? So, right. So again, this example, this is learning example, shows that we're using red. Red will appear in all documents. Red will appear in all documents, right? So we will do this here, right? We have our data in. So remember, this tfidf, right, has this includes all the reds, right? There's always reds somewhere. So this is just for learning purposes. We can see that it's actually right. So it will be a sparse vector, right? Right. So because of course it will have a very low ranking, right? So it will be very low ranking, basically, right? And we can use that to basically add this vector, right? This vector will be provided for each document, right? We have 10,000 terms, right? On each right ranking will have a will have a value, basically. Okay, so let's take a look at this. All right, so yes, so again it's an extremely sparse vector, right? 10,000 values, right? And again so again 1 2 3 4 5 1 2 3 4 5 terms, right? So red, right? Red is always there. So question is, which one is red? We have to look at the, I think, I don't know if the dictionary will be there, but so yeah, 52 I guess is the red, right? 52, right? And it should have a very low ranking, right? So IDF, TF, term frequency. So this is term frequency. This is just term frequency, right? 1 1 1 1. So IDF out, right? 52 looks like, why is this here all zeros? It's kind of question why some values should be more important, apparently, right? Babushka, right? Red apparently. In inverse. It's in because we didn't. Wait, there's more, right? IDF. Where is our? That's TF and IDF out, right? TF out, IDF, right? Inverse document frequency, right? Yes. Okay. So transform, right? So right. So you can do this again. So this represents how important the term is, right? So the red, of course, in this context is less important. Okay, what didn't we cover? We didn't cover word to vec, which is another way of which captures relationship. You know, famous example is king, queen, right, and man, woman, and you can sort of figure out who is king, who is queen, basically from this, right? So very cool thing, but we won't have, unfortunately, don't have time to talk about this today. But you can read about this in the book. So what I want to give you is, of course, assignment, right? So, all right. So we saw the we were able to read the range. So I would like to, of course, bucketizer would be nice, right? And let's see. And also, of course, I would like to do some splits, right? String indexer, right? Yes, string indexer would be nice, right? And maybe. So again, I'm sure you've been working with Alice, right? So again, you already have tokenized Alice, so you can use that, right? So yeah, so let's do this. Taking again, so take first 10 okay, to do. You already have Alice, so you already have it, right? Take using Alice already, tokenized Alice. Take create the f of say first, 200 rows, maybe, well, no, actually of everything, of everything. Again, token analysis, remove English stop words, right? Right, that's from previous example, from weekend exercise, right? You all have it, right? It's very nice. Remove English stop words, and what else can we do, right? And I want to create account vectorizer of words tokens, tokens terms, right? That occur in at least 3 documents. Here that means rows, right? And at least twice, right? On 3 documents, right? And at least on the terms, of course, obviously, and the terms have to occur at least twice, right? No, at least once in each, at least one time, well, obviously in each row, right? So, or maybe 2 times. Maybe let's do 2 times. That will be actually less. We'll get 2, and we'll get lots of. So this will be this. We probably will the results, right? On show, show first, 30 rows, right, of data, right? Okay. Results, expected results. Well, we'll see. Should show many common words, right? Oh yeah, and also print out the it'd be nice to print out the dictionary as well, of course, right? And let's see. Print dictionary. Oh, I think that will be enough, right? All right, that will be enough. All right, thank you. So I'll see you at 9, and we will talk about feature reduction afterwards, right? We create new auto features. We will also want to stop them. All right, thank you.